Welcome! In this session, we will explore a problem titled Strings Differ by One Character, where we dive into an intriguing algorithmic challenge. We'll walk through the problem, analyze approaches, and understand the nuances of solving it effectively. Let's get started. In this problem, we are tasked with determining whether there exist two strings in a given list, dict, that differ by exactly one character in the same position. Each string in the list is of equal length, and the output will be true if such a pair exists, or false otherwise. For input, we are provided with a list of lowercase English strings, and the output is a Boolean value indicating whether the condition is met. Let's begin with an example to illustrate the problem more clearly. Suppose the input list is dict equals ABCD, act, act. Here, the output is true. To understand why, consider comparing the first string, ABCD, with the second string, act. They differ at index 1, where ABCD has the character B and act has the character C. As there is only one differing character between these two strings, the condition is satisfied, and we can return true. Importantly, once we find such a valid pair, we don't need to check further and can stop the process. Now, for another example, let's look at dict equals ABCD, ABCD, ABCD. In this case, the output is false. All the strings in the list are identical, and therefore, no two strings differ by exactly one character. Since the condition is not met, the function correctly returns false. For a more detailed situation, consider the input dict equals ABC, XYZ, def. Here, we need to compare each pair of strings to determine if any two differ by exactly one character. When we compare the strings ABC and XYZ, we find that they differ in all three positions. Similarly, comparing ABC with def and XYZ with def, we see that they also differ in all three positions. Since no pair of strings differs by exactly one character, the output is false. The constraints further clarify the problem. The list can have up to 100,000 strings, each string can be up to 10 characters long, and all strings consist of lowercase English letters. Edge cases include identical strings, which should return false, or strings of length 1, such as dict equals A, B, which would return true. The solution must handle large input sizes efficiently while adhering to these constraints. To solve this problem, let's first consider the brute force approach. The intuition here is straightforward. Compare every pair of strings in the given list and check if they differ by exactly one character at the same position. For this, we would iterate through all possible pairs of strings, compare their characters one by one, and count the positions where they differ. If we find a pair with exactly one differing position, we return true. While simple to understand and implement, the brute force approach has a significant drawback. The time complexity is n squared asterisk m, where n is the number of strings and m is the length of each string. This is because we're comparing all pairs and examining m characters for each pair. The space complexity, however, is efficient at 1, as no additional data structures are needed. While this method provides clarity, it becomes impractical for larger inputs due to its inefficiency. The main limitation of the brute force approach is its inefficiency, especially when the input size is large. To address this, we can use an optimized approach that leverages hashing. The intuition behind this method is to avoid comparing all pairs explicitly. Instead, we use a hash set to store modified versions of each string. For each string in the input, we generate patterns by replacing one character at a time with a wildcard, such as an asterisk symbol. These wildcard patterns allow us to identify potential matches. The key observation here is that two strings differing by only one character will share the same wildcard pattern at the position where they differ. By generating these patterns and checking against the hash set, we can efficiently find matches without performing exhaustive pairwise comparisons. Here's how the optimized hash-based approach works in detail. First, we initialize an empty hash set. Then, for each string in the input list, we generate all possible wildcard patterns by replacing each character with a wildcard symbol, one position at a time. For each generated pattern, we check if it already exists in the hash set. If a match is found, this means there is another string in the input that differs by exactly one character, and we return true. If no match is found, we add the newly generated pattern to the hash set and continue processing the remaining strings.
Finally, if no matching pattern is found after examining all strings, we return false.
This approach significantly improves efficiency. The time complexity is n*m squared, as we generate m patterns per string and each pattern takes m to create and check. The space complexity is n*m, accounting for the storage of patterns in the hash set. While this method requires additional space, it offers a much faster alternative to brute force and is elegant in its simplicity. Another alternative to solve this problem is using a tree-based solution. The intuition here is to use a tree, or prefix tree, to store the input strings character by character while allowing for a single mismatch during traversal. We start by building the tree, inserting each string from the list. Then, for each string, we traverse the tree with the condition that we allow at most one character mismatch during the search. If we find a match during this traversal, we return true. If after processing all strings no match is found, we return false. This approach is efficient, with a time complexity of n*m, since both building the tree and searching through it involve processing each character of each string. The space complexity is also n*m, as the tree stores all strings. However, the main drawback of this method is its complexity in implementation. Handling mismatches correctly within the tree traversal adds a layer of difficulty, making it less intuitive and harder to debug compared to other methods. For this problem, the chosen strategy is the optimized approach using hashing. It strikes the right balance between simplicity and performance. While the tree-based solution is efficient, its complexity in implementation makes it less desirable. On the other hand, the brute force approach is easy to implement but far too slow for larger inputs. The hash-based solution provides a clean and scalable alternative. By leveraging wildcard patterns, it avoids unnecessary comparisons and reduces the computational overhead significantly. Of course, there are trade-offs. The hash-based approach does require additional space to store the patterns in the hash set, but this is a manageable cost considering the significant time savings it provides. Overall, this method is both efficient and practical, making it the best choice for solving this problem. To solve this problem, we need to determine if there exist two strings in the list that differ by exactly one character at the same position. The brute force approach is a straightforward way to tackle this. The idea is to compare every possible pair of strings in the list and check how many positions have differing characters. If we find exactly one differing position, we know the condition is satisfied. To begin, we handle the input. We are given a list of strings called dict. Let's assume there are n strings in the list and that each string is of length m. This assumption of uniform length is important for our comparisons. The next step involves iterating through all possible pairs of strings in the list. We achieve this using a nested loop. The outer loop runs from index I equals 0 to n1, while the inner loop starts at j equals I plus 1 and goes up to n1. This ensures we don't compare a string with itself or repeat comparisons between the same pair of strings in reverse order. For each pair of strings, say s1 and s2, we initialize a counter called diff_count to 0. We then compare the characters of these two strings position by position using another loop that runs from k equals 0 to m1. Whenever we find differing characters at a specific position, we increment the diff_count. After all characters are compared, we check if diff_count equals 1. If it does, we return true, as we found two strings differing by exactly one character. If no such pair is found after all iterations, we return false. Now, let's analyze the complexity of the brute force approach. The time complexity comes from the nested loops. We compare all pairs of strings, which gives us n choose two pairs, and for each pair, we compare up to m characters. This results in a time complexity of n²*m. On the other hand, the space complexity is 1, because we're only using a few counters and iterators, with no additional data structures. There are several key insights to highlight. Firstly, the condition of exactly one differing character is handled by incrementing diff_count for each mismatch, ensuring precision. Secondly, by starting the inner loop from I plus 1, we avoid redundant comparisons, such as comparing the same pair in reverse order. Lastly, we can terminate the character comparison loop early if diff_count exceeds 1, as it's already clear the pair will not satisfy the condition. Edge cases are an important consideration.
If the list dict contains fewer than 2 strings, it's impossible to form a pair, so we immediately return false.
Additionally, for the brute force approach to be valid, all strings must be of the same length. If they differ in length, the character-by-character comparison becomes meaningless. The data structures used in this approach are straightforward. The primary data structure is the input list dict, which provides efficient index-based access for comparing strings. We also use a simple integer counter diff_count to track the number of mismatches between 2 strings during the comparison process. This simplicity keeps the space requirements minimal. To improve the brute force approach, we can consider optimizations. One simple optimization is to break out of the character comparison loop as soon as diff_count exceeds 1. This avoids unnecessary computations for pairs that are already invalid.
Another more efficient strategy involves using hashing. In this optimized approach, we generate variants of each string by replacing one character at a time with a wildcard or placeholder. These variants are then stored and checked for matches in a hash table. This reduces the time complexity to O and *m by eliminating the need to directly compare all pairs. While this optimization isn't part of the brute force solution itself, it's a powerful technique to handle larger inputs more efficiently. The code solves the problem of checking if any 2 strings in the list differ by exactly 1 character at the same position. It uses a hash set to track patterns generated by partially masking each string. For each string in the input list, we iterate over its characters and generate a pattern by replacing 1 character at a time with *. This represents all possible single-character variations of the string. If the generated pattern already exists in the set, it means a previous string differs by exactly 1 character in the same position, so we return true. Otherwise, we add the pattern to the set. If no such pair is found after processing all strings, the function returns false. This approach is efficient, eliminating the need for a nested loop comparison, and operates in O and *m, where n is the number of strings and m is the string length. This is the Java implementation for LeetCode problem number 1554, strings differ by 1 character. The logic mirrors the Python version, using a hash set to store patterns where 1 character is replaced by *. The substring method is used to construct these patterns, and if a pattern already exists in the set, it indicates that 2 strings differ by exactly 1 character. Key differences include Java's explicit type declarations and the usage of hashset from the java.util package. In this example, we are working with the input dictionary, abcd, abxt, abgf. The goal is to determine if any 2 strings differ by exactly 1 character. We start by initializing an empty set called scene, which will store patterns where 1 character is replaced by an ***. First, we process the word abcd. For each character position in abcd, we replace the character at that position with * to create a pattern. At index 0, replacing the character gives the pattern *bcd, which we add to the scene set. Now, the set contains *bcd. At index 1, the pattern becomes a *cd, which is added to the set, updating it to *bcd, *cd. At index 2, the pattern is *d, and adding this updates the set to *bcd, *d, *cd. Finally, at index 3, we get the pattern abc*, which is added to the set, resulting in *bcd, abc*, d, *cd. With this, we have processed the first word. Next, we process the word abxt. For each character position in abxt, we again replace the character at that position with * to generate a pattern. At index 0, the pattern *bxd is created and added to the scene set, updating it to *bxd, *bcd, abc*, d, *cd. At index 1, the pattern *xd is added, resulting in the updated set *bxd, *xd, *bcd, abc*, d, *cd. At index 2, the pattern becomes *d. This pattern already exists in the scene set, meaning we have found a match. Since *d is common to both abcd and abxt, it indicates that these 2 words differ by exactly 1 character. Therefore, we return true as the final output for this example. Now, let's consider a new input dictionary, ABC, def, GSI. We begin by initializing the scene set as empty. The first word we process is ABC. For each character position in ABC, we replace the character at that position with asterisk. At index 0, this results in the pattern *BC, which is added to the scene set, updating it to *BC. At index 1, the pattern *C is generated and added, resulting in *BC, *C. At index 2, the pattern of asterisk is created and added to the set, making the updated scene set *BC, *C, *. With this, we have completed processing the first word. We now move on to the word def. For each character position in def, we replace the character at that position with asterisk to generate a pattern. At index 0, the pattern *EF is created and added to the scene set, resulting in *BC, *EF, *C, *. At index 1, the pattern *F is added, updating the set to *BC, *EF, *C, **F. At index 2, the pattern D** is generated and added, resulting in the updated scene set *BC, *EF, *C, **D**F, **. Next, we process the word GHI. At index 0, replacing the character generates the pattern *high, which is added to the set, updating it to *BC, *EF, *C, **D**F, **high. At index 1, the pattern G** is added, making the set *BC, *EF, *C, **D**F, **high, G**I. Finally, at index 2, the pattern GH** is created and added, resulting in the final scene set *BC, *EF, *C, **D**F, **high, GH**. Since no pattern is repeated across ABC, def, and GHI, we conclude that no two strings differ by exactly one character. The final output is false. In this example, we are given the input dictionary, AAA, OB, AAA. We start by initializing an empty scene set. The first word we process is AAA. For each character position in AAA, we replace the character at that position with asterisk. At index 0, the pattern *AA is created and added to the scene set, resulting in *AA. At index 1, the pattern A** is generated and added, updating the set to *AA, A*. At index 2, the pattern AA* is created and added, resulting in the scene set *AA, A*, AA*. This completes the processing of the first word. Next, we process the word OB. At index 0, replacing the character generates the pattern *, which is added to the scene set, updating it to *AA, A*, At index 1, the pattern *B is created and added, resulting in the updated set *AA, A*, *B. At index 2, the pattern AA* is generated. This pattern already exists in the scene set, indicating that we have found a match. The repeated pattern AA* shows that the words AAA and OB differ by exactly one character. Therefore, we return true as the final output for this example. In this solution, we analyze the time complexity by breaking it into its components. The outer loop runs once for each word in the dictionary, so if there are n words, the outer loop executes n times. Within the outer loop, the inner loop generates patterns for each word by replacing one character at a time with a wildcard character, represented by asterisk. Since each word has a length of m, the inner loop performs m iterations. Constructing each pattern involves slicing the word, which is an O-M operation. Therefore, generating all patterns for a single word takes O-M*M or O-M squared time. Additionally, for each pattern, we perform a hash set lookup and potentially an insertion. Both of these operations have an average time complexity of O1. Combining these steps, the inner loop's operations dominate, making the overall time complexity of the nested loops O(n*M squared). Now let's combine all these components to understand the total time complexity.
The outer loop executes n times, and within each iteration, the inner loop runs m times, generating patterns for each word. Since each pattern generation takes m time, the total time complexity is n m, which simplifies to n m squared. Moving on to space complexity, the hash set plays the dominant role. The set stores all unique patterns created during the iterations. For each word, m patterns are generated, and in the worst case, all these patterns are unique. With n words, the total number of patterns stored in the set is n m. Since each pattern is a string of length m, the space used by the set is n m squared. Temporary variables like the generated pattern only require m space per iteration, which is negligible compared to the space used by the set. Hence, the overall space complexity is n m squared. Let's compare this solution with the brute force approach. In a brute force method, we would compare every pair of words in the dictionary, which involves n*(n1/2 pairs. For each pair, we would check if the words differ by exactly one character, requiring m time per comparison. This leads to a total time complexity of n squared m for the brute force approach. The given solution optimizes this by using hash set lookups, which are constant time operations. As a result, the time complexity is reduced to n m squared. Now, considering best, average, and worst case scenarios, the best case occurs when we find a match early, allowing the function to exit after processing only a subset of the words. Here, the complexity is k*m, where k is the number of words processed before the match is found. However, in the average and worst cases, all words and patterns are processed, leading to the full complexity of n m squared. Finally, let's justify the big O complexities. The time complexity of n m squared arises from the three main factors: iterating over n words in the outer loop, iterating over m characters in the inner loop, and performing m operations for pattern generation. Together, these steps contribute to a total complexity of n m, which simplifies to n m squared. For space complexity, the dominant factor is the hash set, which can store up to n m patterns, with each pattern being a string of length m. This results in a space complexity of n m squared. Thus, both the time and space complexities are driven by the interplay of the number of words, the length of each word, and the operations required to generate and store patterns. When tackling this problem, there are several common mistakes that you should be aware of. First, failing to account for edge cases like empty strings or very small inputs can lead to runtime errors or unexpected outputs. For instance, an empty dictionary or strings of length 1 might not be explicitly mentioned in the problem description, but handling them gracefully is essential. Another pitfall is relying on inefficient brute force methods. Directly comparing every pair of strings in the list results in a time complexity of n squared m, which quickly becomes infeasible as input sizes grow. A third mistake is misunderstanding the requirements, specifically, the condition that strings must differ by exactly one character. Some candidates mistakenly compare entire strings without ensuring that exactly one position differs, leading to incorrect results. Lastly, overlooking duplicate strings in the input list is a subtle but critical oversight. Duplicates can falsely meet the differ by one condition if not handled properly, so it's important to address them carefully in your solution. Another common assumption to watch out for is that strings are always of the same length. If the problem doesn't explicitly guarantee this, failing to validate string lengths can lead to logical errors. Now, in an interview setting, optimization is often a key focus. Starting with a brute force approach is fine, but interviewers usually expect you to propose more efficient solutions. For instance, hash-based data structures can minimize redundant comparisons and significantly improve performance. It's also crucial to clarify constraints at the beginning of the discussion. Ask whether strings are guaranteed to be of equal length, whether duplicates are allowed, and what the maximum input size might be. Beyond this, communicating your thought process effectively is just as important as solving the problem. Make sure to articulate the trade-offs between simplicity and efficiency as you refine your solution. Finally, always test your code with edge cases like empty lists, one-character strings, or lists that include duplicates. This ensures your solution is robust and ready for real-world scenarios. This problem shares similarities with several others in the string manipulation category, which can provide valuable practice and insight. For example, LeetCode 720 focuses on finding the longest word in a dictionary, while 212 involves searching for words within a grid. Problems like 49, group anagrams, and 17, letter combinations of a phone number, also emphasize efficient string operations.
Exploring these can deepen your understanding of related techniques.
Now, when optimizing your approach for this problem, one effective strategy involves pre-computing all possible strings that differ by one character for each input string. By storing these in a hash set, you can check for matches in constant time. The trade-off here is increased space usage, as the approach requires O(m) space, but it substantially reduces the overall time complexity to O(n)(m).
Alternatively, you can consider using a tree-based solution.
This involves inserting all strings into a tree and performing a search to find strings that differ by exactly one character. While tries are memory-intensive, they are highly efficient for string operations, especially when dealing with large inputs where strings share common prefixes.
Another alternative approach involves leveraging a matrix-based pairwise comparison method. Here, you create a matrix to track character differences between every pair of strings.
This allows you to quickly identify which pairs differ by exactly one position. While the method is conceptually simpler than hashing or using a tree, it does come with significant trade-offs. Specifically, it requires O(n)² space and time, which can become prohibitive for large inputs. However, for smaller datasets or scenarios where simplicity is preferred over optimization, this method can still be a viable option. By considering these different approaches and their trade-offs, you can choose the one best suited to the problem constraints and the context of your interview or implementation task.
Great job!
To wrap up, we reviewed the problem's strings differ by one character, summarized the brute force approach, and highlighted key takeaways. Keep practicing and applying these concepts to similar challenges.
Thanks for being here, see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!